Hello everyone and welcome to today's webinar, Advanced Material Solutions for Rod Guides. My name is Mitchell Peeler and I'm here with my colleague Peter Schmieg, and we will be sharing with you advanced material solutions for rod guides. We work on the Specialized Industries team here at DSM Engineering Plastics, and we're excited to present this webinar today. First, we're going to go over a little introduction of ourselves and then a quick little overview of DSM as a whole. So first, to introduce myself, my name is Mitchell Peeler. I'm an account manager for DSM covering the Southeast with an emphasis on oil and gas. I recently graduated from the University of Kentucky with a bachelor's in chemical engineering, and while there at Kentucky, I did some research with biofuels.
Yeah, so thanks, Mitchell. And my name is Peter Schmieg. I'm a senior application development engineer in the Specialized Industries team, as Mitchell had mentioned. I'm actually based out of Houston, Texas, and my focus is in the oil and gas industry. I have 20 years plus experience in performance polymers as it relates to engineering plastics for structural components, and I have a mechanical engineering degree with a background in structures and metal to plastic conversions. So turn it back to you, Mitchell. Go ahead.
Thanks, Pete. So before we start this webinar, I have a couple housekeeping items to cover. We definitely like to hear from you during today's presentation. If you have any questions for us, please feel free to send it in using the webinar's chat feature, and we will answer your questions by email after it's completed. Also, after the webinar ends, a link to it will be shared with you via email, and you can watch the webinar again on demand if you like. You may also forward the webinar link to your colleagues that have an interest in learning about advanced material solutions for rod guides. So let's get started. So just a quick overview of DSM as a whole. So DSM is not just a material company. We're a company that is very diverse, as you can see on this slide. So we cover everything from the plastics that we're talking about today to nutritional supplements, to animal feed, personal care products. So we've got the three: materials, nutrition, and animal feed sectors. DSM is also a global company, so we span across 4 continents. We span across North America, South America, Europe, and Asia, with offices in each, and with production on 3 of the continents. So it's something that we can, all these materials that we're talking about today can span across the globe if that's something that you need. The DSM's also created high temperature. We're really focused in these areas, in the nylons, the PA6, PA66, PA410, PPS, PA46, and then our PPA materials, which is our 4T. So on the next slide, we're going to see the pyramid, but as you can see, the transition, the TGs of these increase based on which chemistry we're looking at. So here's our DSM's product portfolio for materials as a whole. So we stick more to the semi-crystalline side of the pyramid here. We go all the way from Arnite, which Arnites are our PETs and our PBTs. We have our Aculon and Novamids, which is our PA6s, PA66s. Our Arnitel, which is our thermoplastic copolyester elastomers. We have our Zytron and our 4T up at the top, which those are going to be the focus of our webinar today. Those are our PPS and our PPA materials. And then we also have 2 other products: EcoPax, which is a PA410, and Stenil, which is a PA46. So that's kind of an overview of DSM as a whole. Next, we're going to go into the meat of this webinar, and I'm going to let Pete take over from there.
Well, thank you, Mitchell. That was a great introduction and segue into the technical portion of the presentation and design challenges, which I'll be covering here. Looking at the oil and gas industry and kind of checking the challenges there and common material failures, and how DSM's been developing new products to address those common failures for the rod guide market. So when we look at the costs associated with drilling, downtime we know is unacceptable. So when we look at offshore drilling, daily rates are, in the $500,000 just for a rig. And downtime from whether it be tooling failures, pipe, pumps, etc., as well as guides and rod systems, that downtime rate can get up in that 10% range, and that downtime is essentially costing money for those folks that are drilling out there, up in the $7 million, upwards of $7 million downtime per day. So that's unacceptable. And we know onshore or on land drilling has got costs associated with that as well. So this is just taking an example of, in an offshore example. So looking at material challenges within the oil and gas, we've kind of broken this down into structural needs, as well as chemical resistance and temperature orientation. So the first, when we look at fracture and crack analysis, that has to do with essentially structure of the plastic materials within the well system. So when we look at rod guides, the structure of that is, and the integrity, whether it be fatigue, performance, crack, etc., is extremely important. Then, depending upon the location of drilling, we understand that temperature resistance is integral, as well as pressure resistance. So when we look at different depths, whether it be a shallow depth well, 4,000 feet, up to a deep well, going beyond 7,000 feet, those pressures and different environment in terms of chemical environment, hydrogen sulfide, and whether it be a high water cut versus a low water cut well, that takes its toll on the plastic materials for rod guides. So also when we look at different wells, whether it be sour gas, temperature is definitely important. We've heard upward anywhere between 180 degrees Celsius up to 250 degrees Celsius from a temperature standpoint. So it's very important to design materials for the specific need, and that's an area where DSM has been on the forefront in developing new material technologies for our PPAs and PPS materials. And then one of the last but not least, resistance to wear and abrasion. We understand, if we can improve and reduce the wear on the rod guides and how the interaction between the rod and the pipes we can increase the time out in the field without having to pull the pipes and guides. So that reduces the overall downtime. So obviously with design flexibility for high performance materials for rod guides, we understand there are metal rod guides out there as well. However, the industry has shifted towards high performance thermoplastics and composites to offer design flexibility and molding for efficiency's sake. Yeah, and kind of going back to the pyramid here, as Mitchell touched upon our product portfolio from DSM, I'm going to take a little bit different approach, looking at what materials lend themselves for the oil and gas industry. And on the right-hand side, the crystalline materials really are key for focus for DSM, and I know for the oil services and the energy producers, that right side of the pyramid is extremely important because it's the crystallinity of the products that give the performance, whether it be temperature, chemical resistance, abrasion, and wear. You'll see, obviously, as you go up in the pyramid, temperature and performance when you get into the PEKK and PEKK type materials, temperature resistance and chemical resistance notwithstanding, are excellent. Good wear performance as well, and you'll also see PPS in the foray when you get up into the higher performance. The other is high temperature nylon materials, the PPAs, which are semi-aromatic nylons, and then you'll also get into the aromatic, or excuse me, aliphatic nylons, which I'll touch upon as well, with PA6, PA66, and to a certain degree or to a lesser degree, polyacetyl. But PPAs and PPS are good from a chemical resistance standpoint, also have very good good wear performance, and kind of fit in the good temperature and performance range as well. So next I'd like to touch upon the PPAs versus aliphatic polyamides. PPAs are semi-aromatic, so what that allows us to do is increase temperature ranges, whether it be melting temperature of the material, as well as glass transition temperature, the TG, and that's a very important indicator for mechanical performance in the well, or how the material will perform, or the part is going to perform in the well. So by increasing the aromatic content, you're able to bump up the TG. When you have low TG range of 90 degrees C up to about 130 C, DSM's actually worked on development of even higher TG materials, which I'll touch upon, in the 150 and 160 degrees C range. And that has some important benefits as it relates to chemical stability, dimensions, high temperature performance, also blister resistance. In a segment that DSM is very ingrained in is the electronics industry, and they do a lot of reflow soldering, so low moisture absorption for PPAs, the ability to reduce the blistering due to moisture in the material, and due to that reflow soldering, because they do a flash reflow about 260 degrees C. So by reducing the moisture in the material, you can reduce that blistering effect. That's just an example. Some of the challenges that we understand with PPAs, and we're able to mitigate that by different technologies in the material. They're very, very stiff, but typically have lower elongation than aliphatics or long short chain polyamides. Also, the weld line strength is a bit lower, as well as typically wear performance is lower. But I'll be showing you, some of the wear performance of these new products, new materials that we've been developing for the rod guides. It's quite intriguing, as well as it's typically more challenging from a processing standpoint. And there, it's not difficult, but it's just more challenging from a standpoint of being able to control the molding machine and the melt of the material. So yeah, getting into the material selection, I'm going to focus a little bit of my time here on PPAs, and not all PPAs are created equal. What DSM has done, when we look at our PA46 or polyamide 4,6 type material, DSM has a 4-carbon chemistry, and the 4,6 uses adipic acid. So it's a very symmetric molecule or monomer unit, and it's highly crystalline. So what we've done is we've essentially replaced the adipic acid with the terephthalic acid to get that cyclic ring structure to make it an aromatic. And we have the ability, because of the carbon 4 chemistry, to increase the aromatic or the terephthalic acid component quite high to improve the TG, chemical resistance, as well as improve wear performance again. So this is one of the key differences, I would say, between the aliphatic and aromatics. So choosing the right PPA for the application, when we talk about low TG PPAs, glass transition temperature below 100 degrees C, and that has typically lower aromatic content and However, it does give better flow for some of the electrical and electronic component that we supply into. And it has the ability to use water heated tooling, so not a need for either high pressure water or even oil heated tooling for that matter. However, when you bump up the aromatic, when you get into some of the higher TG materials, the stiffness goes up, moisture absorption goes down. That also has an impact by improving the chemical performance and temperature performance. However, it does have a slightly lower processing window, and yeah, it requires oil heated tooling to maximize the properties of the material. So looking at the 4T PPA portfolio, and the 4T is DSM's trade name for our PPAs, we have a whole host of products for different markets that we serve, and that just kind of gives you a brief overview from electronic to automotive electronics, as well as metal replacement. So when we focus in on the oil and gas industry, we have a number of materials, but the key focus for our rod guides is our 4T MX15HR material. Has excellent chemical resistance, improved part strength, and very good processing. The column on the second column on the left there is the 4T materials. Those are traditionally lower temperature PPAs. The 4T ACE products have glass transition temperatures up to 150 and 160 degrees Celsius, depending upon which grade we're talking. We also do offer extrusion grades and unfilled grades for injection molding and extrusion. And again, that technology for rod guides is also in play today when we talk about coated pipes for downhole. So next, I'd like to really jump into the low wear and low friction grades, because the one thing that we have found in for rod guides is limiting or reducing downtime for wells. And if we can increase coefficient of friction and reduce the wear of the rod guides, it has an important effect on how that guide is going to wear on the steel or the metal tube or the metal pipe. So 3 grades that we focus on. The first one there is our 4T ACE. It's a high TG PPA. That is actually an unreinforced. We have that available for sampling. Has good wear performance and chemical resistance, and is also a toughened PPA. So that's a product that we use for coated pipes. Not so much uncoated pipes. That's where we focus more on the 4T MX15HR. That has very good TG, 145, and that's commercial material. Today it's 35% glass filled PPA, so it has very high part strength, but actually better wear performance than what traditionally has been out in the market today for PPAs. And the third material there is our Zytron G4010E. And you'll see that's also commercially available. That's a 40% glass filled PPS material. That has very good wear performance and best in class chemical resistance. So again, we've done some tribology measurements, which I'll get into shortly, which we benchmarked some of the existing PPAs in the market today. And we are very excited about these materials. So one of the things that DSM has done is we've taken some of our thrust washer measurements. This is actually done on a Lewis research tribology equipment, and we've done an ASTM D3702. So basically what this is we're taking the injection molded thrust washer on a steel mating surface, and this is a rotational test. And the output of that test is to look at coefficient of friction, as well as we characterize the height loss in that thrust washer over time under certain PV conditions. You'll see in this particular example, this is something that we've done for specific customer for rod guides out in the industry. We've preconditioned samples at 93 degrees C for 24 hours in 100% or in water. And the test itself was conducted, as you can see there, at 55 degrees C in a high humidity environment. So that was in a 100% relative humidity. So we've characterized for this unreinforced 4T ACE product, that's an unreinforced PPA, we get our measurement for coefficient of friction and our wear rate, as you can see on that lower chart on the right there. We've done the same thing for our glass-filled PPA. This is a 35% glass fiber reinforced product. It's our MX15 HR, so it's a hydrolysis resistant, highly chemical resistant, but has very good wear properties. So we've done the same thing. Conditions are the same from the previous example, the unreinforced example, under the same conditions and same PVs. And again, this is our PPS material. This is a 40% glass-filled product, and in the other case, for the PPA, we also are targeting glass fiber reinforced. DSM has other materials which we're looking at right now for even additionally lower wear with some of the exotics, carbon fiber, as well as aramids. So when we look at the glass-filled PPS, we again run through the same general test parameters. So I'll come back to that shortly, comparing that data to existing PPAs on the marketplace and PPS in the market for rod guides. But our 4T ACE PPA, this is looking from a base polymer perspective, and you'll see that pink line there, or the pink graph, is the 4T ACE PPA. So comparing that base polymer, that's a high TG PPA, 150 to 160 degrees Celsius. We are able to improve the mechanics by bumping up the aromatic content, and that has a significant play in how the performance of that mechanics is above the TG of the material. So comparing to traditional PEKK product, again, these are all base polymers. These are all unreinforced. So we look at above the TG of the products, the 4T ACE has a very good mechanical property profile above TG and up to beyond 200 degrees C. The other thing is when we look at chemical resistance, so understanding that the 4T ACE, this is some testing that we've done in sulfuric acid for 1,000 hours at 100 degrees C. So the 4T ACE product maintains its mechanical properties after aging at that temperature. So it's very, very good from a chemical resistance perspective. So we know in hydrogen sulfide and high water cut wells, and the combination of the two, the 4T product and the 4T ACE performs quite well. So chemical resistance notwithstanding, the 4T lends itself quite good to the oil and gas industry. So next, I'd like to target or focus on some of the material comparisons to what's other PPAs out in the market. So we benchmarked um, current rod guides, and what we found is this is the unreinforced 4T PPA. So mechanical properties are very, very similar. However, due to the technology of this material, this is the wear and friction testing that I showed previously, that thrust washer test. The wear rate is a significant reduction by up to 3 times to the competitive PPA. Coefficient of friction is also quite good here and actually reduced versus what we've seen in the past. So looking at the 35% glass-filled PPA versus a 33% competitive PPA, which is traditionally, again, used for some rod guides out there. Mechanical performance, you see, when we look at tensile modulus, tensile strength, very comparable. Actually, the 4T is slightly higher. That might be due to the additional couple percent glass, but overall, very good impact resistance. But pay particular attention to the wear rate. Again, we see wear rate improvements and drop quite dramatically with this particular material. Coefficient of friction is close to the competitive PPA even with the additional glass loading, slightly additional glass content. So next, this is looking at our unreinforced ACE. This is the NC271184 product. As previously mentioned, PPAs are highly stiff material. So when we look at comparing the ACE product to another high coefficient of friction, low wear material, the Stenil TW441, that's benchmark for wear and friction applications. We see the stiffness for the 4T ACE above the glass transition temperature quite good. So what's important to know when choosing the right product for the application is to understand what temperature range we're playing in, as well as what the environment is in play. So Stenil is a more hygroscopic material, so it would pick up more moisture than the 4T. So this is one of the reasons why the ACE product is positioned for oil and gas and downhole applications. And what you see by these two pictures over on the right-hand side, that's actually a tensile bar. And for normal PPAs, it's very difficult because they are stiff to twist and turn a tensile bar like that. So, you know, in the case of high stiffness, high TGA, unreinforced material, the 4T ACE still maintains its TG and high stiffness, but also flexibility in an unreinforced material. So yeah, next, just kind of wanted to more or less summarize some key takeaways that I just discussed. We looked at low TG PPAs versus high TGA PPAs and some of the differences relating to processing, mechanical performance, tensile properties, as well as chemical resistance. When to use PPS materials. So when we look at PPS, when we have high chemical resistance environments, PPS is typically specified in those applications. So when we look at the benefits of PPAs over PEKK and PEKK in oil and gas applications, it's very important to understand which environment we're competing against there. The thing that we understand with PEKs and PEKs versus what we're positioning for PPA, our PPS product, or Zytron, as well as 4T, is the cost differential versus the PEKK type materials. Were significantly lower in cost, so it makes it a nice material to choose for high volume applications such as rod guides. So in summary, we have a whole product portfolio, a broad portfolio with a number of different materials, but we have key developments that we've undertaken with our PPA and PPS products for reduced wear for rod guides. So if you would like to learn more about DSM, we have dsm.com or DSM Plastics Finder. You can go to this website and get additional information on the materials, and you can also feel free to follow up with Mitchell or myself. We're happy to take any questions you may have, as well as any emails if you have an application that you'd like us to review. So in conclusion, I'd like to thank you for joining Mitchell and myself for the DSM Plastic webinar about advanced material solution for rod guides, and we hope you enjoy the presentation. And for more information about DSM Engineering Plastics and to access the DSM white papers and blogs written by our subject matter experts, please visit Plastics, or for more information, as just mentioned, please visit www.plasticsfinder.com. Thank you for joining, and enjoy the rest of your day. So thank you for joining us today for the DSM's oh geez. Can you cut that out? I just messed up. So thank you for joining us today for DSM Engineering Plastics webinar about advanced material solutions for rod guides. We hope you enjoyed the presentation today. If you'd like to get some more information, you can visit dsm.com /plastics, or Plastics Finder has a whole host of information, including DSM white papers and blogs written by our subject matter experts. Or you can contact either Mitchell or myself, and we'd be happy to answer any questions that you may have or follow up on any applications that you might be interested in speaking about. So thank you very much.